So if we go to this one next, what I'd like to notice is, first of all, the domain. Are there any restrictions here? Can I raise any number I want to the fifth power and then take its cube root, positive, negative? Same thing with raising to the second power and taking a cube root. I think I can. So I think the domain is going to be all real numbers. There's no square roots here, right? Square roots are a problem. You can't take square roots of negative values. But cube roots, you can take cube roots of anything. Let's look at x-intercepts and y-intercepts. The y-intercept is a matter of setting x equal to 0. I think it'll be 0, 0. X-intercepts is a matter of setting the whole thing equal to 0. Actually, let me go off to the side and do this. For the x-intercept, we're going to say that x to the 5/3 minus 5x to the 2/3 is equal to 0. We're going to factor out an x to the 2/3 power, and that's going to give us an x to the 3/3 power, which is silly. I'm never going to write that, am I? Because it's really just x to the first minus 5, so I can get rid of that. That means that x equals 0 or x equals 5. So I've got x-intercepts at 0, 0 and 5, 0. Symmetry, this guy has no symmetry whatsoever. You can plug in a negative x. You're not going to find any symmetry there. I'm just going to say none and not spend the time on it right now. If you want me to explain, talk to me during office hours. Same thing with horizontal asymptote and vertical asymptote. These are not rational functions, so we have none in both cases. Let's go ahead and find f prime and f double prime and find some critical numbers and possible points of inflection. So the derivative, I've got 5/3 to the subtracting 1 would give me 2/3 power minus 10/3 to the negative 1/3 power, which I think we probably need to rewrite this in such a way that's going to allow us to determine where the derivative fails to exist and where it equals 0. So what I'm going to do is I'm going to rewrite it as 5x to the 2/3 minus 10/3x to the 1/3 power. In order to make a common denominator, I'm going to multiply by x to the 1/3 power here and here. And that's going to give me 5x minus 10 over 3x to the 1/3. F prime of x equals 0 when x equals 2, right? If x is 2, the numerator is 0. F prime of x does not exist when x equals 0. So we have critical numbers at 0 and 2. All right. Let's go ahead and find f double prime and find possible points of inflection. F double prime of x. I'm going to take this version here and just multiply down in front. So the 2/3 multiplies the 5/3 to give me 10/9. X to the negative 1/3 power, subtracting 1 from the exponent, plus 10/9 again, x to the negative 4/3 power. Again, I'm going to need to set this thing equal to 0 in order to find the possible points of inflection. I'm going to make a common denominator. I'm going to multiply here by x to the 3/3 and x to the 3/3, and that will give me 10x plus 10 over 9x to the 4/3. Now I'm going to find my possible points of inflection. F double prime of x equals 0 when x equals -1. We also have f double prime of x does not exist when x equals 0. So possible points of inflection are x equals -1 and 0. All right, we've actually done a lot of good work here. I'm going to go ahead and I'm going to start making my table. To make the table, what points do I care about? Well, obviously I care about my critical numbers because I could have a change in increasing, decreasing on either side of those. I also care about my possible points of inflection because those are potential places where we have changes in concavity. So my table, again, I'm going to put my intervals vertically. We've got -infinity less than x less than -1. And then we want to identify what's happening at x equals -1. The -1 less than x less than 0. And then we want to identify what's happening at 0. 0 less than x less than 2. That's our other critical number. And again, we want to identify what's happening at x equals 2. Might be a local max, might be a local min, might be neither. And then finally, 2 less than x less than infinity. We're going to find f of x for certain points. We're going to find f prime of x, whether it's positive or negative, and f double prime of x, whether that's positive or negative. And all that will hopefully give us some worthwhile conclusions. Let's go ahead and plug in -1, 0, and 2. I think we already plugged in 0 way up there at top. So we already have that this is 0. If we plug in -1 into the function, f of -1 is going to be -1 to the 5/3 power minus 5 times -1 to the 2/3 power. Raising to the 5th power, -1 to the 5th is -1. Cube rooting it is -1. Taking -1 and squaring it gives us +1. Cube rooting that is still +1. So I think we get a -6 out of that. F of 2, I'm going to spare you the excitement here. I got that approximately equal to -4.8. So we've got these three values. Now we want to check f prime and f double prime. So again, just like we did before, maybe we can come up with some sort of pattern that'll make our lives a little bit easier. So f prime of x is equal to 5x minus 10 over 3x to the 1/3. And we're going to plug in values in each region. So -2, for example, -1/2, right? I'm just plugging in values in each of these regions here. F prime of 1, f prime of 3. So the denominator, if you notice, it's a cube root. It's going to be positive when x is positive, but it's going to be negative when x is negative. Basically, I'm noticing that the denominator is going to take on the same sign as whatever I plug in, into my function. In the numerator, when I plug in -2, I get -10 minus 10, that's negative. When I plug in -1/2, I'll have -5/2 minus 10, which is negative. When I plug in 1, I get 5 minus 10, which is negative. And plugging in 3, I get 15 minus 10, which is positive. So I've got a positive here, a positive here, a negative there, and a positive there. I also know that f prime of 2 is 0. I know that because it's one of our critical numbers. So this is a 0 here. And I think if I try to plug in 0 into my derivative, I get an undefined value here. Now we need to look at f double prime, 10x plus 10, and on the bottom, I have 9x to the 4/3 power. Now the 4/3 power is making me very, very happy because that means I'm raising the number to the 4th power and then taking a cube root after that. But what happens when you raise a number to an even power? It always, as long as it's not 0, it's always
Positive.
Yeah. So that's done. And then on top, if I put in a -2, I'll have -20 plus 10. If I put in -0.5, I have -5 plus 10. If I put in 1, I have 10 plus 10. If I put in 3, I have 30 plus 10. So that's a negative, meaning concave down, followed by a whole bunch of positives, meaning concave up. And from there, if you were to plug in 2, f double prime of 2, I think we get a positive over a positive again. So I get a positive in here. Now, let's write up some conclusions. Looking at the first derivative, that means we are increasing, decreasing, and increasing. And looking at the second derivative, that means we are concave down, concave up, concave up, concave up, also concave up here, really. What does it mean if at this point in green, we are going from concave down to concave up? That makes that point in green what? It's a point of inflection, that's right. Point of inflection. Good. Now let's look at, I don't know, this point here in yellow. I've got x equals 2, right? -4.8. And they're telling me that I've got a horizontal tangent line and I'm concave up. What does that mean if I have a horizontal tangent line and I'm concave up? Desiree, using the second derivative test, is telling me it's a local minimum. That is correct. So this is a local min. You can also notice that by looking at the fact that we are decreasing followed by increasing at that point. So I can't wait to see what this graph looks like. I know you're excited too. So let's see what we can do here. I'm going to start off by plotting some points. 0, 0 is a point on this graph. -1, -6 is a point on this graph. 2, -4.8 is a point on this graph. What am I missing here? Oh, I also had an x-intercept, didn't I? Way up there at the top, 5, 0 is also a point on this graph. Boy, that's a funky looking graph. Hang in there, we're almost done. What do we have? We are increasing and concave down, right? That's the first interval there that I'm trying to point at, is increasing and concave down. So here comes increasing concave down up until that point. Then we have a point of inflection followed by increasing and concave up. So watch the way I'm going to draw this thing. I'm increasing and concave up like that. Okay, it might be a little hard to tell with my horrible drawing here, but there's a change in concavity from concave down on this first portion to concave up, and we're increasing the whole time. Then we've got, oh, look at that. We've got increasing followed by decreasing. This is going to be a local maximum. And then we are decreasing in concave up. So that's going to look like this. And then we hit a local minimum, and then we're increasing and concave up, which is going to look like that. And believe it or not, there is your graph. It seems like it seems pretty wild. We haven't seen one of those before, have we? It almost seems like I'm just making things up and this isn't really real, but I'm going to show you that it is. It's very exciting. Oh my gosh, look at that graph in green there. Doesn't that look very familiar? I think we did it. Mine is far more beautiful than the computer generated graph, of course, but that's it. That's the graph. Now you can clearly see that we have a local max at 0, 0. You can clearly see that we have a local min here at 2, negative 4.8. You can see the y-intercept. It's not as clear seeing that this changes from concave up to concave down here. That was at the point, what was that point? That point was -1, -6. So -1, -6. That's the point where it switches from concave up, concave down. I'm going to try to manipulate the graph a little bit so you can see that a little bit better. It might not work very well, but let's see. You can kind of see, here, let me do it a little more. Like that. If I switch this over and zoom it out, maybe we can kind of see, no, that's not, it's even harder to see. This is a concave up-ish. Let me do this. This is concave down, and this is concave up. Example 4, we've got another polynomial. In this case, f of x equals -x to the third plus 9x squared minus 15x plus 2. Starting off with the domain, since it's a polynomial, the domain is the set of all real numbers. Next, we'll look at the x-intercepts. So we've got to take this function and set it equal to 0. Immediately we notice that it's not clear how to factor this polynomial. So we're going to go ahead and use the rational roots theorem, which we've seen back in pre-calculus. And the basic idea here is we're going to come up with the set of all possible rational roots by creating this fraction p over q, where p is all the integer factors of the constant term, and q is the set of all integer factors of the leading coefficient. And we notice that p in this case would be plus or minus 1 or plus or minus 2, because those are all the integer factors of the 2 and back. And similarly, q is simply going to be plus or minus 1, because those are all the integer factors of the -1 leading coefficient. And then we make all the possible fractions out of these values where p is in the numerator, and we get plus or minus 1 over 1 or plus or minus 2 over 1. So we have 4 possibilities of rational roots for this polynomial. Now, for 1 and -1, it's probably easiest just to plug them in and see what you get. For example, f of 1 would be this, which is -5, which clearly doesn't equal 0. Plugging in -1, we'll get 1 plus 9 plus 15 plus 2, which again, there's no way that's 0. So these guys are no longer candidates. But positive or -2 could be roots of this polynomial. So now let's see if 2 is a root of this polynomial. If it is, that means that x minus 2 is a factor of this polynomial. So we could divide this polynomial by the factor x minus 2 using long division, but let's go ahead and use synthetic division this time. For synthetic division, for this x minus 2 factor, we're going to write a 2 here, and then we're going to write all of the coefficients of the terms like this. And if you remember how this works, we bring the -1 down below. And the idea here is that we're going to take the 2, we're going to multiply it here, and then we're going to write the result right there. In other words, we get a -2 right there. And then we add straight down, and we're going to get a 7. And again, we're going to multiply the 7 and then we're going to write the result right there. And that gives us a 14. Then we add straight down, and we get a -1. And we multiply here. We write the result right there. That gives us a -2, and we get a 0. And that 0 basically tells us that we don't have a remainder. So now our polynomial is looking like x minus 2 times, we've got our squared term coefficient here, so that's a -x squared. We have our linear coefficient here, so that's plus a 7x, and then we have our constant here, -1, and all of that equals 0. Now for this trinomial, again, it's not going to factor, so we're going to go ahead and use the quadratic formula. So we're going to have x equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a. This will give us two different x values. Putting these into a calculator, we get approximately 6.9 here and 0.1. So those are going to be our x-intercepts. We're going to have 2, 0, 0.1, 0, and 6.9, 0. The y-intercept we get by plugging in 0 for x, and we get 0, 2. Vertical asymptotes, none, because we don't have a rational function. Same thing with horizontal asymptotes, none. We could talk a little bit about end behavior. We can just notice that since this function has an odd degree and a negative leading coefficient, that the end behavior is going to look something like this, going towards positive infinity for the y values as x goes to negative infinity, and going to negative infinity for the y values as x goes to positive infinity. All right, let's go ahead and get some derivatives, find some critical points, and some possible points of inflection. So we have -3x squared plus 18x minus 15, and that's going to factor nicely for us this time. So we have critical numbers at x equals 1 and 5. And then taking a second derivative, we get -6x plus 18, which if you want, you could factor that, I suppose, and get, what, x minus 3. And then we have possible point of inflection at x equals 3. All right, so now we're going to go ahead and build our table using our critical numbers and our possible points of inflection. So our first critical number is 1, so we're going to create an interval from -infinity, less than x, less than 1, then see what's happening at x equals 1, and then our next point of interest, shall we say, is the possible point of inflection at 3, so we'll go 1 less than x less than 3, x equals 3, and then 3 less than x less than 5, x equals 5, and then 5 less than x less than infinity. So these are our intervals. We'll have a column for f of x, f prime of x, and f double prime of x. So first, finding the corresponding y values for our critical points and our possible point of inflection, we have to find f of 1, f of 3, and f of 5. I got -5, 11, and 27. You can pause the video and check those out on your own. Now, if we look at our first region, x between -infinity and 1, if we were to plug in, say, 0 into here and here, we would have a negative times a negative times a negative, giving us a negative here. Plugging in 0 here would give us a negative times a negative, which is positive. Moving on to the region for x's between 1 and 3, so maybe we plug in 2. If we plugged in a 2 here and a 2 there, we would still have our -3 times, this would be -3 times 1, which will give us a positive here. And of course, plugging in 2 here would give us -6 times -1, which would be positive. Skipping down to the region for x's between 3 and 5, if we plugged in 4 here, we would get a -1, and a 4 here would give us a +3. So we'd have a -3 times a -1 times a +3. That's going to be positive in this region here. And then plugging in a 6, let's say, if we plugged in 6 here, that factor would be positive, that factor would be positive, and we're multiplying it by negative, so that gives us a negative here. Going back to the second derivative, I should have plugged in a 4 here, which would have given us a negative, and also plugging in a 6 there would also give us a negative. So looking at where we have a negative for the first derivative means that we are decreasing. A positive means we are increasing. Again, a positive increasing, and a negative decreasing. Now, looking at concavity, we have a positive here, meaning we are concave up. Same thing here. Here we are concave down, and here we are concave down. And so looking at the conclusions for what happens at our critical numbers and our possible point of inflection, you'll notice right here we go from decreasing to increasing. And so by the first derivative test, that means we have a local minimum right there. And looking down here, we go from increasing to decreasing, meaning we have a local max. We also could have noticed that right here, if we would have put in 1 into the second derivative, we would have gotten a positive, meaning that we were concave up and we had a horizontal tangent line because it was a critical number, making it a local min. And similarly, we could have done that here, plugging this into the second derivative, seeing that we have a negative, which means we are concave down and we have a horizontal tangent line, meaning that we have a local max. So that's second derivative test, but we already figured that out from our previous work. So now we're ready to go ahead and see what this graph looks like. So plotting the points that I know, first of all, looking at the table, I've got 1, -5, so that's maybe about there. We have 3, 11, so that's maybe about here. And we have 5, 27, which is maybe way up there. Then we also have some x-intercepts from earlier, which those were at 2, 0.1, and 6.9. So we have an x-intercept here at 0.1, which is really close to 0 there. And then, what was it, 6.9? 6.9, so we'll put that maybe about there. And then we also have a y-intercept, which is at 0.2. So that's maybe about right there. Okay, so looking at our first region here, we are decreasing and concave up from -infinity all the way to 1. And so that's going to come down, decreasing, concave up. It's going to look something like that. Okay, not the best work. Maybe I'll try again, but that's the idea. We're concave up, going through these 2 points like that. And we notice we have our local minimum here. And then we're going to be increasing and concave up. So we are increasing here and concave up all the way to this point here. And we notice that we switch from concave up to concave down. So in between those, we have a point of inflection. And so that is this point right here is a point of inflection. And now we are going to increase and concave down. So that maybe looks something like that. We hit our local maximum. And then we are decreasing concave down through that x-intercept And that should give us the rest of our graph. And so we have the point here, 1, -5 is our local min. We have the point 3, 11 is our point of inflection, and we've got a local max at 5, 27, and there's our graph. So go ahead and do the next problems.